practiced well on the weekends. Uh, Today is our sixth day of certification program on machine learning and GenAI. So I hope up to this level you have learned all the basic concepts of machine learning and basic uh, using a Jupyter Notebook or Google Colab, how to uh, text, how to code a basic programs of machine learning, basic algorithms of machine learning. So today we will see the basic concepts of deep learning. A little bit, all the fundamental concepts and what is deep learning. The agenda of today's program, today's session. So here, the starting, we will learn all the fundamental concepts of deep learning, and then we'll see why deep learning come into picture. When since machine learning has so many advantages, then still why we need to go for a deep learning. Third, we will see where that idea comes of deep learning, or how we will use the deep learning concept. And then we'll see some basic mathematical concepts of deep learning. So deep learning mostly works, base is your foundation should be mathematical background. So some fundamental concepts we will see, mathematical concepts we will see in deep learning, like scalars, what is the tensor, what is the matrix, and different types of matrix we use in our coding and we are programming. And after that, we will see the main, the main terms in deep learning are hyperparameter and parameter. And what is the difference? How we will define that two in our coding language. So all these things we will see in our session. Let's begin. First, what is deep learning actually? So first we will go for machine learning. So already told you machine learning is nothing but the machine can learn something by itself with a human effort. If we, as a human, we will give some features to the machine. If we want the machine to learn a image of dog, we will give some features to the machine, and then machine has to learn that is a dog from that given features, and it has to predict that is a dog. So that is nothing but machine learning. But if the dog image is like, suppose I have trained the machine with some features like fur color or skin color or some eyes, the type of eyes and the shape of ears. So all these things I have given as features for the machine, and machine learned it very well. I have showed so many pictures of dogs. It learned so well, and then in the testing level, it has predicted well as it is a dog. Now I have given a new picture of dog wearing some type of different clothes, or dog wearing some cap, or dog wearing something different, and half dog only I am giving. So what will happen? Whether you think machine can able to predict that is a dog, because whatever it learns from the images is completely with some different features. So there should be some there. It has built some relation between it. It has built some relation between the input and feature and input and output. But when the image is when the input given is completely different, then sometimes machines cannot able to predict that using a traditional machine learning algorithms. For suppose I'll give you one more example. Suppose my aim is now I have to predict a image of some 9. I want my machine to predict handwritten images of the numbers. So I have given all these type of images like 1, 2, up to 9 I have given to the machine. And machine trained well, and while testing it is predicted 9 well. But now I have given the image like this. do you think whether the machine can able to predict this? No, because the image is rotated completely. That machine cannot machine cannot able to predict because while giving the input data, while giving the features, we didn't tell that the image can be rotated or the image. Now the new input, whatever I am giving, I gave like this, something like this, something like this I have given. Only up to this amount I have given, see, like this. So these things also the machine cannot able to predict because this is a scaled image that is completely aligned to the left. That machine cannot able to predict. Or one more example is suppose we are doing a analysis of some sceneries, environmental pictures. I took that so many environmental pictures and I want to train the machine with all that sceneries. So in scenery, if you see so much of greenery on the backside, so if you give the features, the machine may confuse that if both the greeneries, there won't be any much difference. There won't be any much difference, and machine may confuse between the two pixels. The immediate pixels it may get confused if you use normal machine learning algorithms. So these all cases, what is the main thing? Machine learning will not able to predict a complete new features. Whatever features we are giving to the machine, depending on that only, it will learn its algorithm. The machine will be trained and it will build the logic. So that is where machine learning is lagging. So main thing is features. So to make it proper, the deep learning comes into picture. So the main advantage of deep learning is the feature extraction. So whatever features the machine learning cannot able to predict, that deep learning will able to predict. So the same image here in deep learning, the all the features will be created like a layers, so many layers. So it will create, this is the global features, means whatever we can see, that directly we can see whatever features we can see, that it will create as a global features. Then whatever features we cannot understand as a humans are something hidden features will be there. So maybe here the white color is there, edges will be a white colors. So this feature it can able to learn by itself and it will create that feature in one more layer. So edges should be white. One more feature it will take by itself. That we didn't do. So deep learning main purpose is feature extraction. So with the whatever features we have given to the machine, along with that, it will create some more features and it will able to predict the inner in depth of the data set. It can able to analyze in depth of the data set. So that is the main difference between machine learning and deep learning. So mainly feature extraction is the main difference between machine learning and deep learning. Now, now the now deep learning is a that's why we call it as in the starting class. I told you AI is the complete just like a global. In that we'll have a machine learning. So AI is completely prediction everything, and finally whatever decision you are taking, whether the robot can move or not, to take the decision, that is AI. In that the correct prediction will be the ML. So machine learning. In that ML, if ML also unable to predict if the large data set is there, very large data set is there, and we cannot able to give the complete features, then we will use deep learning. So deep learning is a subset of machine learning, which can able to extract the features. And machine learning subset, which is proposed to learn from the data features automatically like the human brain. In other words, it repeats the human brain functions in artificial method to process and classify data by effective self decisions. So deep learning is mainly based on artificial neural networks. It's just neural networks. So deep learning, whatever you want to do a algorithm on deep learning, that's completely by neural networks. So what is a neural network? We will see. So just assume how, suppose I am teaching now to you, and without my knowledge, I'm just moving my hands. How I can able to move my hands like this? Because something in my brain is telling that while teaching something, you take this action. So sometimes, if you observe, sometimes I am moving my right hand, and sometimes I am moving with my left hand. But it's not intentional. Automatically, it will happen with my brain. So something is there in my brain that depending on my voice, depending on my whatever content I am delivering, automatically the hand movement will be there. So that part is called some neurons. Some neurons are working. So this is the biological neurons, what will happen in our brain. So biological neurons, if you take, so there are so many inputs here. Here you can see. So these are dendrites. So dendrites are the inputs from different locations, and it will come into a particular cell. This is called a cell body. So all the inputs are given to a cell body first. So the same thing is mimicked here in artificial neuron. Whatever neural networks we are using in deep learning, this is the artificial neural network. So the same thing mimicked here. So we are taking so many inputs from different locations, and we will give this X1, X2 things to this some processing unit, just like here the cell body. In the processing element, we will add the summation of the inputs, whatever we are taking, and some bias, the product of some weights and the inputs we will take, and we will sum everything here in our cell body. I'll tell you why we are taking the weights here, but this is just like cell body. Then after coming to this cell body, then whatever I am doing just now, I am talking something, so my brain will give some information to my hand. So some action it will give, some instruction it will give. The instruction will be given by this processing element. Then that instruction will be passed to my hand nerves that you move this hand like this. So some action is going to take here. So the particular things whichever going to take action here in my hand are called activation functions in our artificial neural networks. So this is the cell body, and these are the activation functions. So depending on the information given by this cell body, this activation functions will take the action. So now for my example here, the hand, in that hand, the nerves will be the activation functions. So sometimes these activation functions will work, and sometimes these activation functions will work. So that depends on the instruction coming from the processing unit. So here from the instruction will come here. And what I have to move, sometimes maybe in both the hands I have activation functions, but sometimes depending on my voice quality and my the frequency, maybe these activation neurons should be very low. These should not act. In that cases, the information will be given to particular neurons will be stopped at some point. They will not activate. So there will be some condition, or we call it as a threshold here. So depending on threshold values, this activation functions will give you the outputs. The threshold values will be dependent on which type of activation function you are using there. So each activation function will have a threshold value. Once the threshold value is reached, then the output will be generated from this neuron. So in this way, this is the block diagram of one artificial neuron. So these like this, so many neurons are added together, and it will be formed like a layers, and different layers will have. So depending on that, each and every layer, the output will be generated. So this is the working of a neural networks and what will happen in deep learning. And one more thing is, once the output is generated, now we will compare this generated outputs with our original output. Suppose the same dog image we are taking. So we know output as dog. Now this is the predicted output. Now we'll compare all these outputs, the summation or average of all these outputs with our actual output. If there is any loss, if there is any difference is there, more difference is there, then again we will come back to the first here weights, and we will adjust these weights. Weights means each neuron will be given to some importance. Maybe while talking, I have a 6 neurons in my brain. So in that 6 neurons, while now, if I am talking now means only second neuron and fourth neuron should be activated more to talk. Maybe first and third will not be activated more. So depending on this, the importance will be given like in numbers. So this neuron should be given some 30%. This neuron should be given some 30% weight, 20% weightage. Like that, some weights will be assigned at the randomly at the starting level. Once the process is completed, at the end, the outputs will be compared with the actual ones. If the loss is more, then come back and now adjust the weights. So if loss is more means the weight, whatever importance we have given to this input is less. Now you increase the weights. If we have given more importance to this neuron, so you decrease the weight. So like that you change the weights, then again process the complete thing and then check the outputs. If the outputs is okay now, very near to our actual one, then the model is completed. Otherwise, again come back, again change the weights. So this happens for each and every neuron and each and every layer. Then and each and every completed all the layers up to when you'll get the loss as minimum. So this is the working of our deep learning neural networks. This is the basic working of deep learning neural networks. Now, so here while talking about neural networks, so generally we have 3 layers. So first one is an input layer where all inputs from different locations will be gathered and summarized in the input layer. So there itself we will add weights. We will add bias. Bias, I'll tell you in while doing the program why we have to add a bias each and every time when you are doing the neural network program. And the second layer is hidden layer. So hidden layer, all the process will be worked. Whether we have to summarize each and every input with the weight, and then then what activation function should be added, and at what time the activation function should be operated, and like that everything will be done in the hidden layer. The complete controlling unit part is the hidden layer. So all the process will be worked on hidden layer. From the hidden layer, the output will be given to an output layer. So 3 layers are default in neural networks. One is input layer, one is hidden layer, and one is output layer. So in the output layer, we will get so many outputs from each and every neuron. And depending on the function, whatever we are taking at the output layer, whether we are going to take all the probabilities, which one is maximum probability, that output you can consider, or you will take the average of all the inputs. Like that, we will take depending on our application, and we will predict the output. This is the basic, working of deep learning algorithms. And this is the difference between machine learning and deep learning. So in machine learning, to learn the relationship between features and patterns, there is statistical rules and regulations. Like if it is a linear regression, we will use y equal to mx plus c. If it is a logistic regression, we will use 1 by 1 minus 1 plus e power minus y, like that. But in deep learning, it is the algorithm will learn itself the relation between, it will create the features and it will create the relation between the input and output. There won't be any special mathematical relations. The features also created by algorithm, and of course the relation also created by the algorithm. There won't be any mathematical relations. And second one is machine learning's maximum we will work out for a normal data. It's not completely smaller, that's a normal. But if the data is very larger and completely unclean data, most of the things we cannot able to understand also from the data. Sometimes in real data will be like that only. In that cases, deep learning works better. And it's a low level task. And here it's image processing and natural languages. Mostly deep learning thing will be occurred useful in image processing and natural language processing and sentimental analysis. So if you take the sentimental analysis, same feature face with with my face, machine learning, what I features I can give my face, my nose and my some face structure, shape, all these things I can give. But if you are doing a sentimental analysis with the same features, I have to generate so many images with different emotions. So machine learning may not able to predict with the same features. There, deep learning comes into picture. It will create different features of smiling, sadness, angry, all these sentiment, emotionals. It will create different features and it will predict. So mostly in sentimental analysis, natural language processing, and image prediction, we will go for deep learning. And this machine learning mainly for the training, it will take very less time. But deep learning, it will take more time. In deep learning, normally we use epochs. Epochs means for each iteration, how much time it will take. Sometimes if it is a larger data, if you give 100 epochs or some 10 epochs, from morning to evening, it will take time. So it will take very no more time for the training. But the accuracy will be more in the deep learning compared to machine learning. And less complex and easy to interpret the result. We can see easily the result. But this is more complex. And sometimes we are unable to understand the result and understand the concept in deep learning. That need more and more practice for the deep learning. And for the machine learning, the CPU is enough to store the memory or no, but very high on large data if you are going, you have to go for GPU. CPU is not enough for deep learning problems. So these are the basic differences between machine learning and deep learning. So these are the layers, whatever I have explained. So each and every neuron will have this structure. So like this, each and every neuron will be there. So this is the input layer. This is the hidden layer. And the third one is the hidden, one more hidden layer. And this is the output layer. So any hidden number of hidden layers we can use in a any number of hidden layers we can use in neural networks. So here I have used two hidden layers. And one input layer. See here, the red color means this neurons for a particular application, this neurons is activated more. So while doing the probability, while doing the actions, maybe to predict something, this neuron is more effective, more influence of this feature is more on this output. So this is activated more here also, and here also, and here also. So this feature and hidden layer, these two features are activated more, and this is giving the output like this. Show you one more example. This is one example for the deep learning. So here I have taken an image of different people faces. Maybe while working this same example, we will see better. But anyway, this is a screenshot from that result. So here I have taken a faces images and I want to predict exactly the faces, the same the faces features I want to predict using a deep learning. So here I have the input layer and this is the hidden layer 1 and hidden layer 2 and output layer. So for human side, I have given the Now faces are patterns. One feature we have given, or if this image we have given as a feature. This image I have given for a feature. So deep learning algorithms, what it will do, it will divide. First, it will divide what type of features I have to take. So here it is taking first patterns, the local, depending on the grayscale or color image, the brightness, depending on that, it is taking the patterns first. Where the grayscale is there, where the black color is there, like that. Second features, it is taking the particular features. It's not concentrating on the grayscale or black colors. Only it is concentrating on particular faces. And third, it is only concentrating on face. Here it is face features. Maybe face shape or where the eyes are located, how much length the nose is there. So this is face features. Here it is completely concentrating on the face. So aggregating all these type of features, it will give the output layer. So the structure is completed here, the pattern is completed, and the color is completed, and face is completed. So like that, deep learning algorithms will divide the features. Now we will see some basic concepts of deep learning. Then while doing the programming or syntax, you have to know, suddenly I'll tell this is the perceptron algorithm we are doing. So you have to know what is a perceptron. All these basic terminology you have to know before doing the lab session for deep learning. So first thing is artificial neurons. So artificial neurons, we call it as a perceptrons. So what are the inputs we are giving? What are the input features it is taking? The inputs. So that are called perceptrons. So perceptrons means inputs. Whatever inputs we are observing from the environment, or the robot is moving in an environment, what inputs it is taking as a feature. So that things are called in neural network language, that things are called perceptrons. The basic building blocks of a neural network inspired by biological neurons. Each neuron receives input, processes it, and added weights, and of course applies an activation function to the produce and output. This complete process is called a perceptron algorithm. Well, perceptron neural network. So this complete program is called, and taking the input, adding the weights, and processing that into, summarize that product of weights and inputs, and giving the activation function and giving the outputs. The process is called a perceptron layer. So in that algorithm, we have three layers. I have discussed already. Input layer will have the inputs, and the hidden layers will consist of all the mathematical, all the functionalities on that layers, and output layer will give you the output. Second one is activation function. So I already told you activation function is nothing but that function will tell you which neuron should be activated at a particular time. From which layer? Every layer will consist of an activation function. So if suppose we have a three hidden layers, after input layer will have one activation function. Then after that one hidden layer. Then again one activation function. Then one more hidden layer. Like that, after each and every layer, we have to incorporate one activation function. So activation function will give you which neuron should be activated at a particular time. So now my activation function will give you on which neurons should be, which neuron of my finger should be activated while talking something. So maybe sometimes this finger will be activated and sometimes this finger will be activated. Like that, neurons also, activation functions will work on which neuron should be activated. So there are generally in programming, in general, whatever the application, these are the basic activation functions we use in our programs. First one is sigmoid. So sigmoid function will be like a S curve. Sigmoid function will be like a S curve. So this thing we have discussed in our logistic regression. So this works only always between this 0 and 1. it won't come at the down negative part, it won't take. So it will assume a threshold value of 0.5, and whatever is above the 0.5, it will assume these values as near to 1, and whatever the values below 0.5 will be activated like the points will be taken as 0. So it works between 0 to 1, and normally this is used for binary classification. I told you binary classification or binary, when you have only two variables in your output, then we call it as a binary classification. Only two variables we have to predict. And next thing is ReLU. ReLU is actually, it's if it is a negative value, if it is, whatever may be the value, negative value, then it will create as 0. So it will take it as 0. Only positive value means it will consider. And tan h, this is the function normally we use for in between the hidden layers. So there, if negative values are there, then to avoid the overfitting or to reduce the complexity, instead of using a sigmoid, we will use the ReLU. This is the best activation functions for the complex problems. Image recognition, image classification, image processing, we will use ReLU function normal. And tan h, it works on the -1 to 1. So whatever may be the negative values also it will be considered. So compared to ReLU and tan h, the complexity of tan h will be more. But sometimes in some cases we have to consider the negative values to analyze the data or to create more features. Then sometimes we will go for tan h, but most of the times we will use ReLU. And this is softmax. This generally applied for the output layer. After coming this input layer and hidden layer, and we have an output layer. So after coming from this output layer, here we will use softmax activation function. So why we are using softmax means softmax normally it won't give you a normal integer number. Suppose here in output layer I have two neurons, and this neuron is giving somewhat like 0.08% output, and this is giving 0. Something like 0.03. 0.03. Instead of giving a integer number, softmax convert that into probability. So it will take probability of all neurons. So whichever is more probability, whichever contains the more probability, then it will give that output as predicted output. So normally it is used for output layers. Maximum output layer we will use the software. And mostly it is important in multi-classification. Multi-layer classification, there are so many variables we have to predict. In that cases, we cannot consider only this maximum integer numbers. There should be some probability. Depending on probability, we have to increase or decrease our weights. So in that cases, softmax that we will see while doing the program. And now, so next thing is forward propagation. So forward propagation is nothing but just moving from layer to layer, from input layer to hidden layer, then hidden layer to output layer, in between using all these activation functions. That is nothing but a forward propagation. And loss function is nothing but, loss function is the machine completely train itself, features are extracted from the images, and the machine has built some layers using a deep learning algorithm, and it is predicted something. Then the comparison between the actual value and predicted value. The difference between the actual value and predicted value is called a cost or loss. Already I told you in machine learning while doing the linear regression. So that loss function that we have to reduce, that should be minimized. So our main goal of either it is ML or DL, any algorithm, the main goal is to reduce the loss, and we want that machines also predict like humans. It should be, if it is a dog means 99% it has to predict that is a dog, whatever may be the image. That is our aim. So that loss function we have to reduce. So there are generally two types we use for our deep learning. One is mean squared error. This we have seen already in our linear regression. Means while doing R2 squares, R2 score for our regression problems, there we have calculated the mean square error, mean absolute error. I told you there. So this is the one thing we use to calculate the loss function. What is the loss at the end of the output? And one more thing is cross entropy loss. So cross entropy loss normally we use for classification. Classification almost there will be some discrete outputs. There won't be any dependency to calculate the probabilities or integer values. So there we will use the cross entropy values. So that is one type of class we will use for classification task, and MSC we use for regression task. These are the two main things we use for loss function. Back propagation. So when if we are talking in neural networks, artificial neural networks, there are generally two types of algorithms we have. Perceptron algorithm is a general algorithm, and feed-forward networks and back propagation algorithm. So in feed-forward networks, there won't be any back. So just we will go in the forward direction. First input layer, then activation function, then hidden layer, then activation function, then one more hidden layer, then activation function, and output and activation function. This is the way of how I feed forward. But back propagation algorithm will have a feedback system. So we will compare that loss function, and then loss functions will be the amount of loss will be given to the weights. So input given to the input layer. So automatically the weights will be converted, the weights will be updated. Then again, the process will be continued as feed forward. Then back propagation will differ with the feed forward in feedback system. So the feedback system will be more important in back propagation. So here in back propagation, the main thing is weight update. So while giving back, the weights will be updated. Weights is nothing but just the importance of the neuron. Which neuron should be important for a particular application? Which neuron should be activated? So how much percentage should be given for a particular neuron? That will be just like weights. So that will be updated. Maybe on the first neuron, the weight may be 20% in the starting level. Randomly we have chosen, but that should be given some 90% weightage. So now we will update that into 0.9 from 0.2. That is the updation of weights. That will be updated depending on the feedback. And gradient calculation is nothing but gradient descent already I told you learning. While learning to minimize the loss, how much fast it is going on a curve. Suppose if you draw a loss curve from predicted to actual, I mean actual, the difference between actual and predicted. If you draw a graph, how much fast you are going to minimize that. So that is called learning rate. So that curve is called a gradient descent curve. So how much fast it is learning the machine. Whether it is learning that in the starting upper side, it has to learn fast. And at the start, in the down, when it is coming to a minimum local, then it has to slow down and the learning rate should be very minimum. That machine has to know at what particular time, what should be the learning rate and how much fast I have to go. That is nothing but gradient calculation. So where I have to give more gradient, where I have to give less gradient. And next one is optimization algorithms. One more important concept in deep learning is optimization algorithms. So optimization algorithms, here we are going to see stochastic gradient descent in our regression algorithms by using regression and deep learning. And one is Adam. Adam mostly used for images. When you are working with images, the gradient descent algorithm is mainly to minimize the loss. Just to derive the loss function and equate to zero. That is nothing but a gradient descent algorithm. For that, Adam is one more type. when you are working with the images, you are going to use the add. This stochastic gradient descent is when you are working with the continuous outputs. When you want to do some numerical data or continuous algorithm you want to do, then you will go for stochastic gradient descent algorithm. Next important concept is learning rate. So learning rate I already explained you, defined by alpha. Normally, we while doing the mathematical concepts, we denote the learning rate with a symbol of alpha. So at what how much speed the machine is learning to get minimum local. The minimum local means the difference between actual and predicted should be zero. And how much time, how much fast it is learning. So maybe at the starting level, the learning rate should be more. When it is reaching down to the local minimum, the learning rate should be very small. So that learning rate we have to give. That is one more important topic. And alpha, every time it will be changed from one layer to another layer. And next concept is overfitting and regularization. These things we will be implemented in our programs. While doing a deep learning program, you have to know about all these things. You have to analyze the graph. Once the epochs are over, once you get the first output, you have to analyze the graph, analyze the plots, and then what technique you have to use and where the problem comes that you are able to understand, you are able to apply. And the next concept is overfitting and regularization. So regularization, I already told you, there are three techniques we are going to use deep learning. L1 and L2 regularization or dropout regularization. L1 and L2 is nothing but we are adding some extra amount to the data, some dimensionality. For the dimensionality, to reduce the dimensionality, we will add some penalty like a something like inverse proportional, some minus sign we will add to that to reduce the dimensionality. Just like for example, if you consider the speed and distance or something like whatever two qualities are opposite in direction or vector. So if one is increasing, one should decrease. Like that, we will add some extra elements to our loss function, which is reversely proportional to that loss function. We will add that elements. So whenever that element is increasing, definitely the loss will decrease. So that we will form a formula and we will use that. So something we will add some inversely proportional to this loss function. So automatically we will increase that penalty, the loss function will be decreased. So that is our aim in L1 and L2 regularization. And dropout means normally in the neural networks. So if I give an image, the machine has to learn the features. So that don't know what the important features and what the unnecessary features. So automatically machine will grasp all the features. So maybe some features are unimportant to that particular algorithm, that particular application. So dropout regularization will find out that unimportant features and it will drop that neurons. Means that neurons are never used in our algorithm. So automatically the space or the complexity of the model will be reduced. That is dropout regularization that we'll see in our program. Overfitting, already I told you, when the machine learns more data, the relation will be built like a complex curve. So when it is built like a complex curve, it cannot able to generalize to the outputs, a new inputs. It cannot able to find out a new input. It cannot able to predict the output. So that is all. Next one is batch normalization. Batch normalization is nothing but while giving you if suppose I have 100 rows of data, some 10,000 rows of data. So instead of giving completely 10,000 rows of data to the machine, what I'll do is I'll divide that training data and in batches I'll give to the machine for the training. So each iteration I'll change the batch. So from each batch, suppose 100 rows of data I have. So I'll divide that into 10, 10, 10, 10. So from each 10 batch, 9 should be a training and 1 should be an output. So each and every data set, every example will work as input and output. So that accuracy and efficiency will be increased by doing that. Next one is CNN. So CNN is convolutional neural networks. Up to now, we have discussed artificial neural networks. So what you are doing, artificial neural networks, directly you are building the neural networks. First, you are building an input layer, and then hidden layers and output layer. But the thing missing there is in the starting, whatever features it is extracted by the machine, you are directly placing that features in the input layer. Suppose the the algorithm extracted some 10,000 features. So all the 10,000 features will be placed in the input layer. But uh, by doing that, the complexity will be increased for a deep learning model. So there CNN comes into picture. So CNN, instead of doing that, first it will do some operation on the features. So suppose I have 10,000 features. So first the mission will work out whether the 10,000 features will be important for an algorithm or not. Then it will reduce the dimensionality. So it will reduce the complete layers. Then we will add a pooling layer. Reduce the dimensionality, we will add a pooling layer. So if the starting dimensionality is some 100 dimensions we have, so first we'll reduce that complete 100 dimensions into some 30 dimensions. Then again we will use a convolutional operation that we will see while doing the program what is a convolutional operation and what is pooling. Then again the dimensionality will be reduced. Then filters will be applied, still reduced. So finally from 100 dimensionality to it will bring into some 4 dimensionality. Then that 4 dimensionality features will be given to input layer. So before working the input, hidden and output, the some feature extraction, feature processing will be done. Feature engineering will be done in CNN. Then the working of the neural networks, normal neural networks will happen. So that is the difference between ANN and CNN again. The next one is RNN. So why RNN comes into picture is RNN is recurrent neural networks. So in CNN, suppose the same CNN if you want to use for a text, if I have a sentence, I have a translation. Some English paragraph is there. I want to know the mission whether it will predict that or not. Suppose just like our Siri, I have to comment something. I have to order something. Siri has to know from the complete sentence and it has to react. So in that cases, Siri should understand what is my first word, what is my second word, what is my third word. So the sequence should be understood by Siri, and then only it has to take the action. If it cannot able to understand the sequence, suppose if I spell like Siri, bring me a coffee. So Siri has to understand the sequence. So if it is not able to understand the sequence, if it is understand bring the coffee something, the sequence if it is not able to understand, then it cannot able to work. So in some cases, in some real-time applications, the sequence should be important. Where normal and natural language processing, while giving this text, some translation, something like in that text cases, we have to remember the sequence. For that, RNN comes into picture. So RNN, all the layers, whatever hidden layers you have considered, that hidden layers will remember what happens in the previous layer. What is the history of the previous layer? That memory will be stored and that will be processed to next layer. In CNN and RNN, that won't happen. That won't remember of the previous layer. Whatever hidden layer 2 don't know what happens in hidden layer 1. But RNN will know about its what happens, what is the history of my previous layers. So then the sequence will be maintained up to the output layer. That is RNN. That we'll see in detail by working RNN. And one more important concept of transfer deep learning is transfer learning. So in transfer learning, just like a CNN or and RNN neural networks only. But what we'll do here, instead of working on the larger data set, first we will work on a small data set. Then we will take a pre-trained data set, a small, very less data set. Then we will apply the same concepts to the bigger data set. That is, we will transfer the same thing to the bigger data set. That is a transfer level. And auto encoders are here. We'll have in auto encoder working, we'll have two things: encoder and decoder. So first it will compress the features. Encoder will compress the complete features and data, and then we'll build the neural networks of layers, and it will work everything. At the last, decoder will be there, which can again enlarge the whatever we have, and then it will give you the output. So it works, compression and expansion works on that basis. And next thing is GANs. GANs is a more advanced of neural networks. So in GANs, we have a discriminator and a generator. So that too will work completely opposite. Like if a picture is there, generator will create the real clean picture of that image, but discriminator will create a malicious picture, a complete noisy picture that will be created by discriminator itself. So both the things will be created. While competing with the two, the algorithm should give you the better picture, best picture. That happens in GANs. So present that we will see in our last day schedule how a GAN works. So how to create a generator and how to create a discriminator. And the next one is reinforcement learning. So reinforcement learning is nothing but works on policies, agent and environment. That is works on rewards and punishment. If the agent works better, it will give reward. If the work agent will not work better, that will be punished. So these are the basic concepts of deep learning. Deep learning. So now we'll move to the mathematical concepts of this deep learning. So now we will take a quiz session, a 10 minutes break. 10 minutes break. Now I'll share you the quiz link. So whatever concepts I have taught up to now, and from this only the quiz session will be there. So we will share you the quiz link. Please attempt, and after 10 minutes we will come back and we will see the mathematical concepts behind the deep learning. Second, we will share the quiz link. I hope you understand up to this. If any problem is there, just please comment in the comment box. If whether I'm going fast or slow, that also you can comment in your comment box. And of course, from tomorrow, we are going to see all these concepts in our lab sessions. Because without understanding the basic, what is layer, what is tensor, now we are going to see all that scalar, tensor, matrix, different operations, what we'll do on the tensor, all these concepts you are going to see now. So without understanding all these things, you are not able to build a neural network. You cannot able to build the layers and how many neurons you have to take in a particular layer, that you won't understand. So today's session will be completely basic understanding of deep learning. Then we'll move on to the mathematical concepts now. And because tomorrow we will work on different, first we will work on the perceptron learning, and then we will work on CNN and ANN. Different types of, pre-trained CNN is there. So we will take some images and we will see how a CNN and RNN work on that. We'll take some sentences and we'll do. So we'll share that link. The link will be shared to you in a few seconds. The link will be shared in a few seconds. Let's have a break. Welcome back. So, uh, welcome back, everyone. And so, I hope you are able to attend the quiz session. So, all the questions, I think everything will be covered in the previous sessions. So, now we'll move on to some mathematical concepts behind deep learning. And most of the members are commenting like my voice is not audible. So I think it's clear now. So if still problem is there, you just comment in the comment box. So now we will see a basic mathematical concepts in deep learning. So in deep learning, I already told you everything is built on neural networks. So neural networks is nothing but just a combination of different types of layers. So each and every layer will consist of neurons, but how a machine will take that neurons? So I have a image. So now the machine ability is to form in layers, and each layer how many neurons should be there and how much should be the dimensionality of the layers. That ability a machine should consist of. I mean, a deep learning algorithm should able to decide for a particular algorithm what should be the dimensionality of a particular layer. Now we normally call that container which stores the data for a particular layer. So a layer, in that different layers will have, and suppose let's say that is a two-dimensionality layer and we have a few neurons in that. So in our deep learning terminology, we call that particular container, we call it as a tensor. So on depending on this name, the TensorFlow is released by the Google. So TensorFlow normally we used for it's a tool we used for deep learning algorithms programming. So normally to do some deep learning algorithms, we have so many tools like Keras. On Keras we can work deep learning. On TensorFlow we can work deep learning. Thano. So many tools are available, but TensorFlow is the most reliable and most efficient on which we can use the deep learning techniques. So that TensorFlow name itself formed using tensors. So tensors will consist of all the data of a particular neurons. How many layers we have, how many neurons we have in that particular neuron, what type of features we have taken. Also, all that data will be stored in a particular container, and that container we call it as a tensor. Now, for these tensors, the tensor dimensionality, depending on the dimensionality, we divide that tensor to few terms like scalars we can call, vectors we can call it as a matrix. So what I mean as a dimension is like a feature. So each feature we consist of an axis. Suppose I want to plot graph between weight and height. There I have one feature, weight, and one predict an output form, a height. So feature have only one integer value have to give. In that cases, that I call that particular tensor is one dimensional tensor. That particular one dimensional tensors in deep learning we call it as vectors. If there is no axis, just an integer number is there. There is no other extra things are not there. There is no need to give anything. So zero axis. In that type of college, it's a real number. It's a integer number only, value only you have to give. In that cases, that we call it as a scalars. So there won't be any direction. There won't be any axis. There won't be any layers we need not to form. Just an integer number is there. In that cases, we call it as a zero tensor, zero dimensional tensor, and it is called a scalar.
Scalar, normally we denote that scalar in our numpy as n dimensional, and n dimensional if it is equal to 0, then we can trace that as a scalar. This these scalars normally we use in a to do while doing working on the continuous output algorithms like regression algorithms. So sometimes we need not to give any layers, or we need not to form any dimensionalities. We need not to form any relation between two things. Just you have to represent some number there. In that cases we'll use these scalars. Second thing is vectors. Suppose vectors is like one dimensional, just in height. I want to predict. I want to give it in height. So there, I have weight is a feature. So I have one dimensionality on one axis. On one axis I can represent the weight. So one dimensionality I have. So I can take a layer of one dimensional like this. So I can represent. So I try this thing as a one dimensional layer. On this layer I'll create the neurons. Whatever neurons I have, I'll create that. So this complete layer will be forwarded to a hidden layer. So first I'll take the input layers, and then this thing I'll take as a input layer, and the remaining I'll forward that hidden layer. So here nothing, no other dimensions are there, only one dimension I have. So this I'll consider as vector. Whenever I have only one axis, one feature only I have to represent. In that cases, I call it as vector. And here, while doing the syntax for these vectors, we can represent n dim equal to 1 while doing the Python programming. So if I have 2D tensors, suppose if you want to represent some pixels, some color I have to represent. Color I have to represent. So in that cases, I have to take some two axis. Suppose I want to, instead of weight, and also I want to consider the person age. Age is one more feature. So this is my age. So on my first layer, I'll have the age neurons. On behind of my age layer, I'll construct one more layer. That is my weight layer. So on weight layer, it will consist of all the neurons related to weights. So I have two layers here. So the dimensionality is 2. So now this I call it as a 2D tensor. 0 tensor, 0D tensor, 1D tensor, and 2D tensor. So 2D tensors normally we'll create that into matrices. So rows and column structure we'll consider that. Normally this thing we generally we use for our deep learning algorithms. Mostly vectors and scalars are mostly nowhere we use, but most of the times we will create the matrix. Depending on that application, we'll use a different matrix, and we'll use the different operations on the matrix. That matrix we will visualize, we will take, and we will consider that on the layers. And mostly in CNN, while before building the neural networks, I already told you we have to do some feature engineering on that features. So while doing the features engineering, we completely use all the 2D tensors in CNN. And now, so next thing is the main attributes. How we will decide a tensor is perfect or not. How a tensor works. So while doing the deep algorithms, the first thing is the rank. Rank is nothing but the dimensionality. How many axes you are giving? How many for a particular algorithm? How many axes you are giving in the input layer, or how many axes you are giving in the hidden layer? So input layer and hidden layer will consist of all the ranks. Anyway, output layer, we don't have that much any access. So you have to know, you have to first predefine how many ranks you are giving. What is the rank of your tensor? So that is nothing but rank. The number of axes means number of features. The number of, in other way, the dimensionality of the features. So that you have to. Second one is shape. So whether it is a 2D tensor, how we are going to represent in your algorithm while doing in your algorithm, whether suppose, if I am giving an audio file. So for the audio file, I can give only rows and axis, column and rows I can give. Or if I want to go for a video file, some video image I am going, then of giving the height and size, I have to give one more axis of the color. So which color I have to give, whether it is a grayscale image or white and black, that feature I have to tell in the video while going to image. If it is normal audio, no need to give that color. So like that, depending on your application, whether you are giving a 2D tensor, whether you are giving 3D tensor. So if it is a 3D tensor, so the shape should be like this. The matrix should be like this. So you have to give the dimensionality here. So 3 size, shape, and here the shape you have to give. This is the 3D. So rank, shape, you must define while doing your program for a particular tensor before building the neural networks, before building the layers. So the third one is date type. Date type is D type. Normally we while doing programming we use that D type. So that thing we have to represent in that particular neuron, in that particular layer, what type of elements you are going to take, whether those are a completely float element, a completely string elements. When you are doing in RNN, this works better. This must actually to do in RNN. So RNN completely works on strings, characters. So in that particular cases, we have to tell that machine in this particular layer will completely have that integer values. In this particular layer will have that complete D type data string characteristics that we have to define. So there every time, each and every layer we have to define D type. So in D type we have to tell whether that is a float, unit, float, everything. And this 32 and 64, that are the number of neurons we use in a particular layer. 32 means that is well, so each and every layer means, what I mean is, in the first layer, in the input layer consists of some 10 layers. Input layer itself consists of again 10 layers. I can call the dimensionality of the rank of that input layer is 10. Means that layers I have combined front and back. So in the layer I have 32 neurons. So here 64 means I have in that each layer I have 64 neurons. So that is the meaning. So whether it may be a float or integer or float, that you have to represent before itself. So these are the main three qualities we have to know before forming an deep learning algorithm. First you have to define, you are able to define the rank, and you have to define the shape of that tensor, and you have to define the D type of the element, what type of element you are using in that layer. So these are the three things we are going to define. And next thing is the vector data. So as I said before, vector data, that is 2D tensors. So vectors is nothing but when you have a two axis, that is called a vector data. For example, if you are doing the student data, so in student database, whether the person will get a placement or not, so that project you are doing, and deep learning you are working. So deep learning you are working, in that cases, particularly the features will be the student percentage in 10th and student percentage in intermediate. That is enough. So two things are enough, and depending on that, we can estimate whether the play or not. So in that cases, that calls a 2D tensor. But 3D tensors are, instead of giving only x and y axis like shape and size, we have to give one more is timestamps. The time steps. At for example, it's a sales forecasting. So on today the sales are this much. So tomorrow, if demand is more, the sales price is the supply is more. So depending on that, so there each and every second, depending on the time, we have to calculate the two features like sales and demand. So like that, with that two features, we are going to calculate, we are including one more thing, one more variable we are including. So that is time stamps, time series data. Normally this thing, these tensors are used in our stock exchange. Mostly in our stock exchange, our sales prediction, our recommender systems. So all these things will apply this concept of tensors, and the remaining will happen. So this is the example for 3D tensors and 2D tensors. So real world example. So second thing you can see, this is the samples, example problems. See, layers will be formed one by one, and these are the features, different features. So one layer I'll have one feature, and this is second feature, third feature, fourth feature, fifth feature. And in including this, along with this, I have included one timestamp. So each and every timestamp will have different layers. So that will be converted into layers. This is the example. And more than 2D are there. So that comes under audios and videos. So images will consist of samples and features are common. Samples and features are common. And with that, samples height and width of the image is common. With that, we are going to use the channels, means image uh, image color. We are going to include that as a feature, extra feature. So will be one layer. So that will become a 4D tensor. And 5D tensors are when you are going for video. So when you are going for video, along with the channel, color, height, sample, feature, along with this, we are going to include the frames. What audio frames, what from which frame to which feature you have to include that video. That we are going to include one more feature. So if any extra feature you want, audio quality or MP4, anything you want to add, that also you can include. So then it will become the dimensionality will be increased more and more depending on your application. So this is about tensors, how we will do the tensors. So this is a few examples on real examples how to create that tensors. This is the most important concept in deep learning. So if you know how to create a tensor, then only after that you create different tensors depending on your application, and you can do the programming. And a batch of data in dataset will be stored in 2D tensor, that is called a vectors, in which the first axis is the samples axis and the second axis as features. So each individual data point in the search dataset is stored as vector. So for example, a statistical dataset of consumers where each individual age, height and gender. These three are the sample features. Since each individual may be represented as a vector of three values, the full data set of 100 individuals can be stored in 2D tensor of shape 100, 3. So here we are giving three features, and the number of examples, number of samples is 100. The shape will become 100, how many dimensional or how many ranks you are giving. That is 3. So that will be represented for the endim or end shape. And a collection of textual information in which each article is represented by the number of times each word occurs in it. A full data set of 50 articles can be kept in a tensor of shape 50, 2000. 2000 words. Here we are using common words while doing the NLP project. So full data set of 50, complete 50, and the common words are 2000. Since each article can be represented as a vector of 2000 values, one count per word in the dictionary. So represented the shape of this tensor will be 50 comma 2000. The complete data samples comma how many dimensions we are going to take. These are the 2000 common words. So each and every word you have to take as an axis. In that complete some 10,000 words, we have segregated the common words as 2000. So that we cannot reduce more. So you have to take the 2000 as 2000 axis. So this is the dimensionality rank the tensor. And these are the data samples we are going to use. So this actually we will use the same shape in RNN while doing the RNN project. So to store the data in 3D tensor with an explicit time axis, whenever time is important, a batch of data will be encoded as a 3D tensor because each instant can be represented as a series of vectors. So may that just example I have considered is stock price data set to. So for this, the shape is this is the 3D sensors. So the previous ones are 2D tensors. So in 2D tensors, we have with the data and the rank. So here, instead of other than the rank, we are including the time series also, time analysis also. So let's see the example. Stock market current value price as well as its peak and lowest prices from the previous hour. So time we have decided. Since there are 390 minutes in a trading day, each minute is encoded as a 3D vector. A trading day may be represented as a 2D tensor of the form 390 samples, comma 3. And 250 days worth of data can be kept in a 3D tensor. So 250 days in that 390 minutes and 3 samples I am giving. So 3 samples are nothing but its peak value, lowest value and the hour value. So the time value. So that 3 axes I am going to consider. Number of samples are 390 and the number of days I am going to consider for this tensor is 250. So combining all these things I am forming 3 tensor. Basically in default while creating the shape, the 2 things should be must. One is creating a data sample and the rank. The remaining things are depending on your application. And next one is for the images. So for the images, it's one dimensional color channel for grayscale images. Even though grayscale images only have a single color channel and may therefore be stored in 2D tensors. That a tensor shape of 32, 64, 64, 1. So this 32, 64, 64 is nothing but a normal pixel, grayscale pixel will consist of the 64, 64 into 64, 32 into 32 resolution. Resolution is 64. So 32 samples and the resolution is 64 into 64 and the rank we are considering as 1. So that's how we will represent a 4D tensor. A batch of 32 grayscale photos means the data size sample of size 64 into 64 means the resolution of the pixels is 64 into 64, while a tensor of shape f1 could be used to store a batch of 32 color images 32, 64, 64, 3. So here we are increasing the rank. Here only we have considered one feature, but here we are increasing the rank. That rank is increased means here instead of considering only one feature, we are considering height of the image, width of the image, and of course the time series of the color pixel of the image. That the rank is increased to 3. This is how we do that 3D tensor. Just now we have spoke about 3D tensor. This is. So here the data samples, how many images we have, whatever images we have, that many images, and width of the samples. This is the height of the sample. See, each sample will consist of, each layer will consist of again 3 channels. So this is one layer, this is one layer, and this is one layer. Now the rank is 3. 3 rank with 3 channels and total of 6 samples. So this is how we represent a tensor. Each tensor will consist of a different feature. This is how we'll represent the tensors. Now, channels, normally these channels we use in our TensorFlow programming. And here on the channels of first formatter, two standards or shapes of, piano also we'll use that channels in the same way we'll use in TensorFlow and the Theano. In TensorFlow, normally we represent with TF dot, whatever shape you are taking, whatever n dimensional you are taking, that will represent after TF dot. TF dot placeholder, TF dot TF dot variable. So whatever maybe you are doing on that tensor, particularly in TensorFlow, we use that as TF dot. And this is how we represent again the pixels 34, 32 into 1, 64, 64. This is represented in our TensorFlow. This is represented the way represented in Theano. One more tool we use for normally deep learning work. If it is a 5D tensors, so up to now we have seen the 3D tensors. Now if it is video can has a set of color images called frames. So different frames will be there in video. The various movies can be saved in a 5D tensors of shape, samples, frames, height, width, and color and depth. So 5 features we are using here. Samples and height, width, color are common in our image data set also. 4. The extra thing here is the frames. At what point of time to which point of time we have to stop that channel. That you have to know before doing an algorithm. So that is called a frame. That frames you have to give. And then it will become a 5D tensor. The series of frames can also be saved in 4D, just removing the only representing only frames, not like samples. Complete sample, instead of representing a complete sample, 1,000 sample, just you can represent these many frames are there. In that particular frame we have these many examples we have that you can represent. So either you can represent in 5D or either you can represent in 4D. So for example, 240 frames would be present in 60 seconds, 144 in 256 YouTube video clip sampled at 4 frames. So some resolution of YouTube video can be just sampled in 4 frames. So 4 of these video clips would be saved in a tensor of shape like 4 comma. So 4 frames comma 240 total of 240 frames. In 144 into 256 is the resolutions. 144 into 256 is the resolution of the video, and I'm giving the rank as 3. So here I'm representing the height, weight, and the frame, not concentrating on the sample. So 3. So these are the things how we represent a video sample. There are 106, 168, 320 values in all. The tensor would store 405 MB in the D type of the tensor was float 32. Since each value would be recorded in 32 bits, because they aren't saved in float 32 and often greatly compressed. This anyway a bit confused here, that you'll understand while doing the program, that we will see in the program, but just understand that if it is a 0D tensor, if it is a normal integer value or some real value we are deciding, that you call it as a 0D tensor. If only two features you are two axes you are representing, that will be a 1D one feature you are representing, that is a 1D tensor, and only two features you are representing, the rank is 2, and that is a 2D tensor. And further, if the rank is 3, then definitely you have to give the shape of the tensor. So shape will consist of first the number of samples, then the resolution of that particular thing, either resolution or if it is a other than image, then we have to represent the height and width, the dimensions of that particular element, particular variable, and then the rank of the element that should be represented in a 3D tensor. So first should be the sample number of samples, how many number of samples you are working, and second one is either if it is a image means the resolution you have to show, or if it is not an image, then you have to specify the height and width, the dimensions of that, and then the rank. These three should be there in a shape of the tensor, whatever it may be, a 3D or 4D or 5D, more than that. This is what we have to know before doing the programs. Next thing is the different type of matrix we are going to apply in our in our programs. In sometimes, particularly while doing the CNN. So as I said, CNN, before doing that algorithm, we have to do some feature engineering. So feature engineering is nothing but a bigger image is there. So in that bigger image, maybe as I said, a scenery, a climate scenery is there. Scenery I'm going to analyze. So in that scenery, that particular image at the last edge side, complete greenery is there. Everything is same in that there greenery is there. So I have to analyze picture. So what I'll do in CNN is I'll first use some filters, some convolutional matrix I'll take. So convolution matrix, some filters, some pooling I'll take. So I'll divide that complete picture into small pixel matrix. Suppose in that complete picture I have 100 by 100 pixels. So that I'll divide into some 10 by 10 pixels. This is one frame. 10 by 10 pixels. This is one frame. 10 by 10 pixels. This is one frame. So each and every frame, then I'll use a filter. A filter I'll use. Filter is a predefined one. Filter will be formed using one of these type of matrices. So that type of matrix we'll use as a filter, and we'll multiply with that filter with that separated frame we have used in our image. Then we'll do some operation. We will do convolution operation. Then the resultant matrix we will compare. Then we will pool that. Pooling means we will reduce the dimensionality. Then we will aggregate all these frames again. We will make a complete picture. So here the starting, if it is 100 dimensionality, then after doing all these things, we will get some 10 dimensionality. So that in that feature engineering, to do that operations, we have to learn the operations on the matrices. So here these are the different type of matrices we'll use in our in that particular feature engineering while handling the images particularly. So first one is square, symmetric, triangular, and diagonal matrices are there. Diagonal matrices are there. Identity matrix is nothing but the diagonal values will be 1 and complete the remaining everything will be 0. See one by one. So this is a square matrix. So square matrix, uh, the, 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 the rows and columns will be same. Whenever you have a rows and columns, if you are using a square matrix for your CNN operation, CNN network algorithm, so you have to divide your complete picture into a square matrix frames. That frame of pixels should be a square matrix. Then only you can apply this square matrix as a filter. So square matrix means the rows and columns should be same. The number of rows and columns should be same. So this is square matrix. So you can apply all these transformation. Either you can apply some rotations you can apply for this, and some inverse operations you can apply, some addition you can apply, some subtraction you can apply while doing the filter operation. Second one is symmetric matrix. So symmetric matrix, you can see that from bottom to top that will be same. either from bottom to top, that will be same. A symmetric matrix is a type of square matrix where the top right triangle is same as bottom left triangle. So if you consider this triangle, it will be same with this triangle. So this is a symmetric matrix. So whenever you want to do a transport operation, then you'll go for a symmetric matrix. And normally, if the frames are completely same in the image, suppose just like sentimental analysis, maybe my smiling and laughing frames will be same, two images will be same. In that particular cases, we'll apply the filter as a transport the previous matrix, symmetric matrix, to get a better result of the filtration operation. Next one is triangular matrix. So this is the triangular matrix. As a triangle will have the values, the remaining values will be 0. For the diagonal, it's a triangular matrix. Here, the shape of this thing is a triangle, the remaining values will be 0. So this is a triangular matrix. Triangular matrix is normally call it as LM, LT, lower triangular matrix, or either you can use upper triangular matrix, but in most of the cases in our programs we use LTs. And LU decomposition, next this thing, while doing the program, I'll explain you this coding and syntax. Trill function, actually it is used to calculate the triangular matrix, and TRIU is upper matrix. If we want to calculate, convert whatever filtration after filtering some matrix you got, that matrix, if you want to convert that into triangular, upper triangular matrix or lower triangular matrix, we will use this syntax, and directly uh, using the Python programming, the matrix will be converted, applied. So next one is the diagonal matrix, is one where values outside the main diagonal has 0 values. So this is my main diagonal. The remaining values will be 0. So here the scalar, if you want to write that is a scalar, so this is a scalar matrix, only values will be there. There won't be any dimensionality. But vector matrix will have a dimension. So D11, D11, D22, this is the index of that row and column. D11, D22, D33. So the direction we have to tell. So two things will be there, either row and two axis, row and column. So two axis you have to represent as a vector. If you want to write the diagonal matrix in a vector, in a scalar means just write the values. Identity matrix is in the main diagonal. If you have all ones, normally this identity matrix will use that for our pooling operation. And of course, in CNN particularly, mostly we have to use that padding to reduce the data loss. So while reducing the image resolution to a lower level, from high dimensionality to lower dimensionality, automatically some of the data will be lost, will be removed. Maybe either the resolution, maybe the clarity of the picture, some data will be missed from reducing the high dimensional to lower dimensional. To overcome that problem of CNN, normally we'll do some padding work. Anyway, that I'll explain while doing the experiment. Padding work, padding operation will do. So in that padding operations, particularly we use this identity matrix. So to main use of identity matrix is, if you do any operation with the identity matrix, the result will not be changed. The result will be same. Just the thing is to reduce some problems, to overcome some problems, will add that identity matrix. Then orthogonal matrix. Orthogonal matrix is whenever you product this matrix with any matrix, the product will be 0. The resultant will be 0. Then that is called orthogonal matrix. Next concept of deep learning is norms. So norm is nothing but the length of the tensor. How much length we are going to take for a tensor. The length of the magnitude of the tensor. if matrix is the pooling, the image is converted into a matrix. Now you want to give the length of the matrix for a particular instant. Then you have to represent that by with a word of norm. So norm size we will tell. On that norm size only, we will add the penalties. So I already told you in the regularization, to reduce that dimensionality, we will add some inverse term like inverse penalty. We will add that. So if that inverse is increasing, the real loss will be decreased. So that's what we do in L1 and L2 regularization. So there, particularly this term will be useful. Norm. So depending on that length of the tensor, we will use the particular inverse length of the norm penalty. The penalty will be used. So norm is nothing but the length of the tensor, a linear number. And norm functions that are characterized by the following properties. So vector norms and negative, non-negative values. And vector norms are zero if and only if the vector is itself is zero. Norms follow the triangular inequality. When a vector is stretched, the norm is multiplied by the stretching factor. So these are the main concepts what we are going to use in our programming language. So there will be vector norms. So vector norms means along with calculating magnitude of that particular tensor, we are have to specify the direction of the tensor. So both the things we have to represent. I mean size and shape we have to represent. I mean and height. So two things, both the things you have to rows and columns. What is the thing in row and what is the thing in column? So both the things you have to represent in norms. So Euclidean norm and L2 norm is nothing but to reduce the dimensionality, you have to predict the length of the tensor. Depending on that length, depending on that distance, there will use the distance uh, length. And one norm, p norm, infinity norm, that we will see in our doing this. So eigen decomposition normally we'll use in PCS, principal component analysis. This thing already I explained you in while doing the optimization techniques. In principal component analysis, to reduce the dimensionality, we have to use how much size is there, how much in what direction it is moving, whether the both the variables are moving in the same direction, whether one is moving up and one is moving down, the input and variable. So if one is moving up and one is moving down, both are inverse direction or both are moving same direction, depending on that we have to add the norm. So there we use that decomposition. So this eigen decomposition is a tool to decide what are the eigenvectors and eigenvalues to add to dimensionality of tensor. That we'll see. Now these are the main advantages of deep learning. These are the basics to learn in deep learning first. Now these are the advantages of deep learning. So first advantage is high accuracy, of course. So it is trained well itself and it will take more time for the training. And then automated feature engineering. This is the best quality of deep learning actually from the machine learning. So features itself, it is extracted and it will decide what algorithm you have to use. And the scalability, flexibility, and continuous improvement. So feedback system will be incorporated in deep learning because the neural networks will have that feedback capacity. So every time the weights will be updated and the result will be better. So unique characteristics of deep learning are it can handle the maximum data. Large data sets will be handled with the deep learning in a very better manner compared to machine learning. And it collects the features from low level to high layers by processing the previous layer. So like RNN, first it will take a global layer, then the hidden features will be taken into account and it will be incorporated more. And then these are the limitations. Few limitations are there. Anyway, that we will discuss in tomorrow's class. Then we'll see some applications and then we'll on to the programming syntax. So now we will share that time is up actually. So we will share the feedback link now. Please give the feedback. I hope you have some basic concepts of deep learning now. So tomorrow we'll see some programs on deep learning, and then we'll move on to CNN and RNN. So good. So goodbye for today, and tomorrow we'll meet again. Thank you. Thank you, everyone.